Hey guys, so I've gotten a lot of questions about learning, reading, retaining things, retaining information, knowledge, like what they are. And I mean, these types of questions are pretty interesting because they make me kind of self-reflect, but also like, you know, I have my own method to my own madness of how like I approach particular problems. But I know some people uh, haven't really matured in the sense of like figuring that out for themselves as well. So hopefully I can. I'm just gonna grab this random book and like read through it and just kind of show my process, I guess. But understanding itself is not something that you get in a book. You can't transfer information from like a book to your brain. Like that's not really how it works. I know like a lot of people might think that's how it works, but um, it's not. That's not really the case because this textbook, right? It's on supergravity, supersymmetry, unification, like all of these things, and it's going to go through gravitation, gauge theory, symmetry breaking, the standard model, effective Lagrangians, supersymmetry, grand unification, petit Salami unification, SO5, SO10, grand unified symmetric uh, groups, and all of these things. Like, there's a lot of information, right? But information in this book is not necessarily knowledge, right? So there's already the author himself already has like this internal network of concepts, intuitions, analogies, and mental images that they're going to go through. And this is a book is merely a compressed encoding of like that network. So your job basically as a reader, especially if you're reading higher mathematics or higher physics, or even I mean mathematical physics is kind of a linear combination of both of those things. Your job or non-linear But your job as a reader is to basically construct your own version of this text in your brain. That's your job. Um, and why rereading the same paragraph 10 times really isn't going to like is going to accomplish very little. Um, if you're decoding the words, right? If you're actively trying to, you know, build the instead of decoding the words, right? That's not necessarily the goal. The goal is to build an internal model that those words are evoking. So that's typically what you would want to do when going through a book. So for me, like, of course, it's always very important to read the preface or the history, whatever section that they talk about. So we have he talks about the SO2 symmetry, algebra, um, and talking about spin and interaction Lagrangians, Pauli matrices, and it just goes through the history of what we've seen so far and sort of the premise of unification, right? So what I'm doing when I instantly look at this, um, spin half baryons and all of these pions, mesons, octets, like these uh, these types of things. For me, as somebody who's done research in particle physics, um, I'm asking why should some of these theorems or why should these constructions be true, right? Well, this is fundamental. So he's going through history, and it's important to have all of these types of objects and like really grind, uh, like and read every word of like how something is being introduced. But then we can go through and let's go to something more exotic like um, supergravity grand unification. Okay, so let's do that. Consider the phenomenon of spontaneous breaking of supersymmetry within the supergravity grand unified models. Okay. Recall that one of our major problems is globally symmetric models, how they arise from massless spin 2 fields, so fermions, basically fermionic fields. The Goldstino after spin. Okay, yeah. I'm not super familiar with this, but that's fine. The analog of a similar problem that arose in non-symmetric theories is the breaking of global symmetry that rise to the Goldstone boson. So they have some kind of motivation, right? And what your brain should be doing when you think, when you're going through more of these avant-garde types of, avant-garde relative to you, right? Is I should be asking, why should this be true, right? Why should this particular approach be true? And if it were false, what would break if it was false? How would I try to prove, or how would I try to prove the I don't know, the value out of this? And what tools seem relevant? So like, even if your attempt to read through this shit is uh you know even if your attempt fails, right, you've created expectations. And so when you finally see some kind of proof, or you see some kind of liner, that uh your brain like has been trying to process, and compare the ideas against your own attempted type of proof, or whatever, own attempted type of here's SC3 cross SC2 cross SC1, so your own like intuition, right? um when you finally see it, the differences will become very informative between your own mental images and the mental images of the author himself. So one small idea can suddenly really reorganize your entire mental picture, and good authors will really find a way to necessitate this, and not only necessitate this, but have a sort of natural gradient towards, when you're reading the book, have a gradient towards those specific ideas. And being stuck also on something, that is the mechanism of your learning. For example, I was stuck for a long time, um, on the assumption, or on, let's say, supersymmetry. Um, Supersymmetry to me was something that was like, okay, why would I care about a particular conditioning a particular geometry on some algebra, right? Why would I care about the Virasoro algebra? And for a long time, I was really stuck between like with infinite dimensional symmetry groups, right? Um, and reasoning through them, right? And like physically reasoning through them. What do they mean? And now I kind of have a better understanding of how they effectively give us Euclidean statistics and give statistical fields, and arise from supersymmetry. Well, gives us ways to factorize particular waves that are analytically solvable, nonlinear waves that then act linearly. For example, the Kurzweil-de Vries waves. And so when I finally found that for me was a condition that, oh, that's what supersymmetry allows us to do. Now we can describe these soliton-like solutions that have these isospectral flows between them. So again, I'm able to do this because I was confused for why supersymmetry even was a thing, right? I was confused where the physics was. And so confusion is not evidence of failure. When you're confused, it's the process where you're trying to build your own understanding and be able to articulate your own understanding. And many people will just interpret this as being stuck at, like, I'm bad at this or whatever, right? Or I'm just bad at math, or physics or whatever. But really, it's just really, you should be thinking is, when you're stuck, you should be thinking, I'm constructing a new mental model. And that's a completely different narrative that is a lot more encouraging also. And when you're trying to genuinely solve something, your brain is identifying gaps and testing and making inferences, reorganizing your prior knowledge. So no solution is going to appear to you immediately, but the useful work in your brain is actually happening when you struggle. Um, but also, mental struggle needs to be productive. So not all struggle, I would say, is equal. Um, let's see. Let's do something that I probably have no idea. See, like for example, if I were to obsess over the Goldstino, right? I mean, I have no idea what a Goldstino is in the supersymmetric uh, formulation of gravity. Okay, I have no idea. This is a new text for me. But uh, let's say proton stability, supergravity. Let's find another one. Um, no, proton stability is pretty important. Yeah. Um, oh no, let's do CP violation. The history of CP symmetry dates back. Charge parity symmetry, by the way. Um, um, so yeah, let's go through and think about what a mental struggle that's not productive. Um, Healthy struggle for you looks like drawing pictures or trying to find specific examples. Here's a CKM matrix. Um, Trying to make conjectures about particular things and simplifying cases between whenever you have a conjecture, like conjecture, trying to simplify cases. And then also, you should be, uh, if you're failing repeatedly, but you have new ideas, right? You're generating new ideas while you're failing. That's good. That's not bad. Just being wrong about something is good. And if you have that generation of ideas, like steady. But unhealthy struggle is when you're reading, let's say, like we're just reading some same paragraph over and over and over again for an hour without changing anything. And if nothing new has happened in 20 to 30 minutes, you need to change your, I guess, the way that you're representing your learning. Okay, and really the true objects that are interesting to anyone who's learning. See, look, we have diagrams here. These things help you understand what's uh, these diagrammatic approaches are very important for physics because they help you simplify these types of interactions and visualize them. Uh, and so, really, this is the true object here. I would argue is the mental images. Well, in combination. So charge, lepton, and supersymmetry. Okay. Um, Really, a manifold or some kind of mathematical object, right? It becomes, or Feynman diagrams or interactions, they become something that you can walk around um, in your brain. And you can think of like, Lie groups as continuous motion, right? Or a stochastic process. This is a family of evolving paths. Or trying to answer a stochastic process is trying to answer um, how does uncertainty itself evolve throughout measurement, right? That's the stochastic process. Like, so these mental images that we have of particular concepts are the true objects themselves. And as experts, really, I've seen this before, that experts report seeing mathematics rather than manipulating symbols. And the symbols merely point towards these internal types of objects that we can do the analysis on symbolically, or whether we're finding some bounds on whatever system um, and constraining it. That is analysis still, So, and another thing that I would like to say is curiosity as well. Like I'm going through this book like in a very curious way, right? That's a way better driver than discipline alone. So if you have curiosity with discipline, that is that will give you the deepest learning because it allows you to come up whenever you have a genuine question that appears, right? So instead of saying, "Oh, I have to finish chapter 5 because I am disciplined to do it." No, 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 no. You want to ask why. You want to always be asking, why does curvature, I don't know, require some connection? Um, I don't know, something like that. Or why can't ordinary derivatives work on manifolds, right? Those types of questions you should be able to ask and then say like that generates your attention naturally because it's like, oh, like now I can go back to chapter 7 or whatever, or chapter something from the book that I read earlier. And so attention really is what determines what gets encoded into your long-term memory. Um, that's the memory part. So lastly, you know, I would like to talk about well, I'll talk about retention a little bit more. But self-doubt as well is pretty universal. So some common misconceptions that a lot of experts um, in a field is that they rarely feel lost at all. But in reality, you know, research mathematicians or research physicists, they often spend days or weeks unsure whether they're making progress at all. And so it requires some level of patience with yourself and some kind of mental, I guess, strength to really see that the difference is that you're not really interpreting uncertainty as evidence um, that that you don't belong anywhere, right? Instead, you should treat it as like an unavoidable part of exploring some unknown territory. And so self-doubt itself is just, instead of saying I don't understand this yet, right? You should say I don't understand this yet instead of I'm incapable of understanding this because I don't know whatever. So the first will leave room for the growth, right? And if you think about just saying I'm incapable of doing this, this just shuts you down and before you even have a chance to work through anything. So that's pretty important as well. Um, Also retention. So just going back to what I was talking about retention. Um, People have asked me like, how do you remember the advanced mathematics, or how do you remember the advanced physics? And the answer is simply, I mean, it's not usually just like uh, take more notes, right? Like, oh, take the more notes. Instead, you should be closing the book after reading it for a little bit and try to reconstruct the theorem yourself, or try to reconstruct some kind of proof and explain the idea aloud, like as if you're teaching it, and then derive it again a day later, and then another day later. So when you reconstruct things, that strengthens your own little network or your own brain's network of like associating different things to make that recall possible. And so when you go through a book and you're reading through this, I might not really understand everything that's going on, but maybe I can find a couple theorems that I could, that I think are very interesting, that are important, and then just kind of close the book, reconstruct it, try to construct the proof again without looking at the book, and then explaining the idea aloud to probably my family that would never, that actually, would, they would probably be like, "What the hell are you talking about?" And it's like, it's okay. I'm doing this for myself, but I'm explaining it out loud. And then just kind of like, recognizing it. I remember seeing this kind of thing, you know, that's much weaker than recalling and being able to say, I can rebuild this from memory, right? So you should probably have about like 10 things or so that are very important to you that you can do from memory. And that uh, build your internal network of your mental images that you have for mathematics and physics. Okay. Lastly, is you want to read with a purpose. You Different books require different reading modes, right? So if you're reading something like foundational, you should probably carefully sequentially read it. But if you look at an advanced book like this, you'll definitely want to read. You'll just want to have a more exploratory cycle that works better. So just skimming the chapter, you know, reading through Neutralino Dark Matter, whatever the hell, reading through the theorem statements, trying to prove them to yourself, building some examples. Read the proof, really looking only for the central insight itself, and then close the book, try to reconstruct everything, and then return later to try to fill in those little technical details and those holes that you might have had in your reasoning. But it's kind of a very messy thing. Okay, so you just have to trust slow progress. You have to trust slow understanding, and by trusting this, a chapter that might take a week, or a chapter itself that might take a month, you might do this to truly internalize, not that you're slow, right? But it's evidence that you're rebuilding a conceptual framework inside of your own mind by spending a long time on something. And so the pace that matters isn't pages, I guess, per hour or whatever. It would be how many durable mental models that you can create. And durable is the key word, right? Like, how many mental models of something can you actually relate to other things? And a useful way to think about this is that every difficult concept is going to begin with a collection of unfamiliar symbols, right? But if you're repeating attempts, over and over and over, with failed ideas, examples, reflections, those types of symbols will gradually become an object that you can manipulate mentally. And so once that transition happens, what previously feels kind of impossible often becomes almost obvious to you. And that transformation itself from the symbols to the internal mental objects then allows you to retain that information and remember exactly how it was done and be able to pick it up exactly where you had left off. So that is the essence, really, of learning higher mathematics and theoretical physics. So thank you guys for watching this video, and I always appreciate the comments. And be sure to join the Discord server as well if you want to interact with the people in there. We have a little community there. So thank you guys for watching. See you next time.